My name is Anthea Muno. I'm not working on information geometry, so I'm a postdoc who works on topological data analysis, so there's some sort of intersection with themes of this conference. I'm working with Sayan Mukherjee at Duke, and neither Garvesh nor Sayan could come to attend this talk today, so they sent me instead. So hopefully I'll be able to tell you about this result and not mess it up too much, but I warn you in advance that I'm not an expert on this information geometry. So I hope that I won't disappoint you too much with this. So the idea here is if you're looking at the optimization of large-scale problems, so what you're looking for is the optimization of some sort of function that takes a vector parameter in RP. And if you're looking at the convergence rate of substandard subgradient descent, we have something of the order of root p, and this is a problem in optimization, in modern optimization in terms of machine learning. And also in terms of mirror descent, we have one of the order of log p, so we have a convergence rate of, this is the convergence rate of the mirror descent, and it's a widely used tool in optimization and machine learning as well. So when we're looking at aspects of differential geometry and statistics, so there's lots of sort of statistical flavors here that we've seen before and that have been mentioned in talks up until now. So one is the Kremerel lower bound. So this is the lower bound of the variance of an estimator. It's a function of the curvature. And we've also looked at sort of Bayesian flavors of this by looking at the invariant priors, so Jeffreys priors. So these are, a non-uniformative a uniformative prior distribution for parameter space based on a differential form. And information geometry in general is the idea of sort of looking at differential geometry of probability distributions. So when we're looking at general sort of optimization, so stochastic gradient descent, so we're looking at this optimization of a cost function, which is a convex differentiable with parameters in a convex set. So the idea of online gradient descent is that the direction of steepest descent is of parameters belongs to a Euclidean space. So this is somewhat restrictive in the sense that parameters don't need to lie on a Euclidean space. So the parameters can also lie on non-Euclidean manifolds. So the idea of natural gradient descent is a sort of generalization to this to allow for flexibility of parameter space being non-Euclidean, and the particular idea of natural gradient descent is to consider parameter space of a Riemannian manifold. So the relation to statistics in this case is that the metric tensor here is determined by the Fisher information matrix. So this is a natural sort of generalization of online gradient descent towards statistics by this relation here. So here, if we're going to do the natural gradient descent, then our updating process looks like this. So the natural gradient algorithm steps in the direction of deepest descent along the Riemannian manifolds. So this requires a matrix inversion, and it has similar flavors to the online gradient descent, but is more generalized to allow for Riemannian manifolds of the parameter space. Another such generalization is known as mirror descent. So here, when you have the mirror descent, the idea is that the updating function is now just some general strictly convex proximity function here. So we have this expression of the psi function. This is our convex proximity function, which replaces this expression up here in terms of mirror descent. So we're interested in particular using the Bregman divergence for our proximity function, which is exemplified here, because it corresponds to the Kullback-Leibler divergence for the exponential family. So this here, that's also something which is very relevant in statistics. So here for the exponential family, if you're looking at normal Poisson-Bernoulli, so here these are going to be the corresponding, so these are our G functions, and the corresponding Bregman divergences look like this for these exponential families in statistics. So right, we want to look at the mirror descent using the Bregman divergence as the proximity function here. And the, sorry, let me just move it a little bit faster. So the idea of this is because the main result of the paper, which will be presented on, is that the paper proves that the mirror descent with Bregman divergence is actually equivalent to the natural gradient step, to the natural gradient step. So if we do that, the proof relies on looking at the convex duals. So if we're looking at the convex conjugate function for a G, then we can look at the extremal point of this dual, and the dual Bregman divergence is defined by this expression here, which depends on this convex conjugate function. And here, if we're looking at the exponential families, and we're looking at these convex conjugate functions and the dual Bregman of that, then we get these expressions here, which are very nice expressions, which depend upon the normal Poisson and Bernoulli again. And it turns out that every Bregman divergence and its dual induces a pair of Riemannian manifolds. So the strict convexity yields a twice differentiable function, so positive definite matrix, and we get primal and dual Riemannian manifolds. And so this shows our sort of equivalence between the mirror descent with Bregman divergence and the natural gradient step. So this is the theorem which was proven by Garvesh and Sayan. So the mirror descent step with Bregman divergence defined by G applied to the function f in the space theta is equivalent to the natural gradient step along the Riemannian manifold in dual coordinates. So the consequences of this in terms of the exponential family with a general density is that we consider the following mirror descent step given by this expression, and then in dual coordinates this corresponds to just minimizing this function here in terms of the Bregman divergence and the maximal point. And it turns out that the curvature of the loss of the Bregman divergence matches the metric tensor. So this particular result allows us to achieve statistical efficiency. So this statistical efficiency, this is defined in terms of achieving the Kremer-Rao lower bound. So it turns out that with this result, the mirror descent step applied to the log loss with step sizes alpha is equal to 1 over t asymptotically achieves the Kremer-Rao lower bound. So this, the idea that Garvesh and Sayan are continuing to work on as a result of this paper is then looking at sort of the information geometry on a mixture of manifolds. So instead of looking at particular sort of Riemannian manifolds, instead sort of looking at sort of different kind when your parameter space is mixtures of Euclidean and non-Euclidean manifolds. They're also looking at the idea of defining proximity functions, so functions over the Grassmannian, as a particular generalization of the manifold. And they're also looking at sort of development of EM algorithms for mixtures. And I'm also supposed to tell them that, say that a lot of money was contributed towards this. And so thanks are supposed to go to for systems biology, Duke, NSF, DARPA, the Air Force, and the NIH as well.
Thank you. I have a very quick question. Was it for exponential families only, or for any kind of probability distributions?
No, it was only for exponential families. But in terms of statistics, this is the one that we care about the most in terms of, you know, it's very relevant to lots of applications.
Okay, any other question? Well, if not, thank all the speakers again.